And welcome to class. Good to see you. It's Wednesday, July 15th. We're starting chapter 22. Homework 7 for this chapter we'll do Friday. We're not finishing today. It'll take a few class periods to get through 22. But test 2 is coming up next Monday, July 20th, 19 through 22. 4 chapters there. Sample test 2 is online, of course. On Friday in class, we'll go over the sample test and, of course, answer questions on it in recitation and office hours. So let's see what we need to do. Before, I'd like to say a couple things. Let's see. Study time and talking to people who did well on test 1. Yeah, so the recommendation for our department is 2 to 3 hours studying for each hour spent in class. So that comes out to 12 to 18 hours during the term. So, and those people are doing it. The people who did well on test 1 are studying a lot, and time is needed for most of us to figure this material out. Also, on quiz 2, there was a questionnaire. It was good to see your background and why you're in this class. I like reading about that. You're a diverse group. People are coming from different majors and different disciplines there. Most of you are pre-professional people who want to go to med school, dental school, and that's great. Even if you're not planning on becoming a synthetic chemist, and we fully recognize that almost all of you are not going to become chemists, and that's okay. But all of you, I think, in the future will be working for organizations and companies involved with organic compounds. The degree to which you understand the fundamentals of organic compounds will allow you to make fundamental contributions to those organizations in the future. So you're learning this material for a purpose, not just to do well on some tests that might be coming up. The final, there's been some questions about that. It will not be an actual ACS final, but it will be actual ACS final questions. It will be cumulative. The topics are over 351 and 352. I have a lot of review materials already on Learning Suite for you. Take a look at that. The ACS, the American Chemical Society, does publish and sell a study guide for the final. I do not recommend getting that. Some people do purchase that. It's $30 or maybe it's even $40 nowadays. We have some older copies in the library. If you're here, you can look at it. But you have a better study guide for the final. It's called your textbook. You've already paid money for that. So stick with that. But review those older chapters as needed. And on the questionnaire and talking to some of you who may not have had that last chapter, chapter 15, in 351 radical chemistry, may need to look at that. But yeah, just a couple general comments there. So let's look at the overhead up here and see what we're up against here. The last chapter for test 2. So carboxylic acid derivatives. These are acyl derivatives where we have a carbonyl and a leaving group on the side. So these are different than aldehydes and ketones. The most reactive ones will be the acid chlorides. We've already seen those for Friedel-Crafts acylation. But here it's how good is the leaving group on the acyl group. Chloride's the best because you can imagine that coming off as an anion in the mechanism, and that anion's very stable, right? It comes from a strong acid, so the conjugate base there is very weak. Chloride anion's weak, so it will be a good leaving group. The next most reactive one will be the anhydrides shown here. This is a symmetric anhydride from acetic acid. They're called anhydrides because they're formed by loss of water. We'll see that. In biology, the most important acyl transfer agents are acyl phosphates or mixed phosphate anhydrides. Phosphate's a very common leaving group in biology, so we'll add that in our discussion. Also thioesters, where we have an ester here, but sulfur instead of oxygen. These thioesters are more reactive, so there's a hierarchy of reactivity here among the structures. And that comes out of the structure as we examine that and what we know about the different atoms that will help us keep track of the different reactions. And then we have nitriles also here. There's no acyl group there. What's up with that? Why are we doing nitriles? Well, it's a carbon with 3 bonds to a heteroatom, which is similar to all these other acyl groups. And plus, nitriles can be hydrolyzed back to the carboxylic acid. That's another definition of carboxylic acid derivative. All of them will react with water. Some will need strong acid or base to go back to the carboxylic acid, but they can all be hydrolyzed back to carboxylic acid. And then the most stable one here is the amides. Now that forms the basis of peptide and protein structures. So amino acids will condense to form polyamide structures, polypeptides we'll call them. These can be long chains with hundreds or even thousands of amino acids stuck together. But fortunately, nature has chosen the amide bond to be the key connecting group there, and that's the most stable one. So yes, proteins are stable. Life would not be possible without the amide bond. Very important bond there. But we'll see esters and a lot of these other ones here. So we'll do some examples, including peptides, proteins, and penicillin coming up. Will be a cyclic 4-membered amide. We'll call that a lactam. There'll be a couple of other common terms we'll have to look at. The mechanisms are all the same. It's all nucleophilic addition, tetrahedral intermediate, and then you got to think about which group can be the leaving group. And that will give you the new carboxylic acid derivative product. And this relates directly to what we've already seen before with the hydride reduction agents and the organometallic reagents, adding to aldehydes and ketones. So that discussion follows directly from that. So mechanistically, all these chapters tie together that way, and I hope you'll begin to see the connection there. This will be quite diverse, a lot of reactions, a lot of possibilities for different reactions. You need to be able to figure out the outcome based on looking at the structure and saying something about the properties of the potential leaving groups there. We'll look at them sequentially. We'll look at acid chlorides first. Those can be made from a carboxylic acid and thionyl chloride. I already showed you that reagent. I won't require you to know the mechanism, although I looked at the book recently, and the book does have the mechanism for thionyl chloride converting a carboxylic acid to an acid chloride. So that's interesting there. But yeah, so then we'll have reactions with acid, water, alcohol, and amines. And so acid chlorides, that's the most reactive derivatives. All the other derivatives to the right here in this figure can be made from the acid chloride because it's the most reactive one. You can make all these other ones from that. And this applies to all the other ones. A thioester, for example, can make all the ones to the right. All the more stable derivatives to its right can be made from the thioester. Esters here, oxygen esters, can make these other ones here. But it's difficult to go the other way, okay? Because these have better leaving groups on them compared to an oxygen ester. So there's a hierarchy of reactivity here, which will limit the types of reactions we can do, fortunately. Otherwise, there'd just be too many reactions to keep track of here. Anhydrides, we can react with water to go to the acid, alcohols to go to the ester, and amines to go to the amides, and we'll look at cyclic ones also. Yeah, this is overwhelming, isn't it? I've warned you, these last couple chapters have a ton of reactions. So we'll look at reactions with carboxylic acids, acid-base chemistry, some cyclic ones, ester formation, both Fischer esterification shown here, and esterification with DCC or carbodiamide. There'll be a separate reagent for that. Esters are very important. That's the basis of a number of things in metabolism, including fat metabolism and many other things. And this esterification reaction of excess alcohol under acid conditions also forms the basis for understanding enzyme catalysis that you'll see later on in biochemistry. So the degree to which you can master this mechanism and understand the aspects of it will really help you moving forward into biochemistry and other molecular biology classes. So we'll go over that in some detail. Esters are very diverse, a lot of applications here. We'll get into a little fat metabolism here, acyl triglycerides. Olestra, I'm not sure I'll talk about that. That's a fat substitute molecule, which is a polyester of glucose. It has 0 caloric content, but it feels like fat in the mouth. So it's been substituted in high-fat foods, but it's had some bad side effects that are kind of humorous. Maybe I'll mention that. I don't know. Saponification, or making soap. We've mentioned that before, but now we'll see the mechanism, which involves reaction of base hydroxide with an ester to form the fatty acid salts, which is actually what soap is. So we'll revisit, I think, the micelle structure and the cleaning action of soap also there. Amides, like I said, are very important here. You need strong conditions to hydrolyze them back to the acid. The basis of penicillin, both the drug itself and the mechanism of activity. So we'll look at how penicillin works, and we'll apply that to the principles we're talking about. Acyl phosphates, ATP, acetyl-CoA, the important cofactor. Thioesters, yeah, also in biology a little bit there. Nitriles, oh, we saved the best for last here. They're different in that it's a carbon-nitrogen triple bond, and we can apply all these other reagents we know to it to make a diverse range of compounds here. It can be hydrolyzed to carboxylic acid, of course. LAH with a nitrile goes to a primary amine. Dibal goes to an aldehyde after hydrolysis with water. And a Grignard reagent goes to a ketone after hydrolysis with water. So very diverse and somewhat different than the other ones, but just as important, I think. Now, here's the main chart right out of your book, this table here. Here's the hierarchy of carboxylic acid derivatives, acyl compounds we've been talking about. Acid chloride, why is that the most reactive one? Well, the leaving group will be Cl minus chloride. That comes from a strong acid, right? So its conjugate base means it's the weakest base, the most stable anion. So that's the best leaving group. And we've talked about that in SN2 chemistry and SN1 chemistry, right? So the best leaving group for acyl reactions is similar there. So here's the pKa's of the conjugate acids. As you see, yeah, super strong acid, -7 pKa. That means that base that it comes from is super weak, right? So your book's reminding you here, increasing acid strength. This is also increasing reactivity here on the right. And then decreasing reactivity, or what? Increasing basicity. So here's a leaving group from an anhydride, which will be a carboxylate. Here's a phosphate coming off the acyl phosphate. Thioester will be a thioanion. And those, yeah, those are more acidic. Thiols are more acidic than regular alcohols. pKa of a thiol here is 9 or 10, whereas an alcohol is around 16, okay? And that's because of the weakness of the sulfur-hydrogen bond and the size of that atom. It's actually against the argument of electronegativity. The oxygen is more electronegative. If that was the only factor, alcohols would be more acidic than thiols, but they're not. It's because of the weakness and polarizability of that bond, which makes thiols more acidic, and will make the acyl sulfides more reactive, or the thioesters. Carboxylic acids, we kind of throw those in different spots, but if the leaving group was coming off there, it'd be hydroxide versus alkoxide, which are similar there. We'll see the different reactions, of course, for esters and carboxylic acid. And then amides, if you pull off a nitrogen with its pair of electrons, that's an amide anion. That's very basic, right? The pKa of an amine to take off its proton from the neutral species and go to the charged amide is 3840. That's different than the ammonium cation. The ammonium cation pKa is 9, okay? We're not talking about that right here. This is neutral. This comes off as a neutral leaving group. That would not be very stable. So this is why amides are the least reactive thing. Also resonance. We'll look at the resonance effects there of all these things, actually. You get to that. Okay, amides. If we got time, we'll go back to this. This is variable temperature NMR, looking at this structure here, dimethyl formamide. We will do the naming of amides and all the derivatives here briefly in a second. But you look at dimethyl formamide and think, well, how many non-equivalent sets are there in that molecule in the proton NMR? Well, are these methyls the same here on this amide? Well, it turns out they're not. At room temperature down here at 25 degrees, there's two signals, one at 2.9 ppm and one at 2.7. These two methyls are different. This one's way down at 8. It's like an aldehyde hydrogen, right? Why the different ones? Well, it has to do with resonance. This lone pair is in a p orbital. The nitrogen's sp2 hybridized. And this resonance effect creates a higher bond order here between nitrogen and carbon, and lower bond order between carbon and oxygen. We can push the electrons here. And if that has double bond-like character, then these two methyls become different. See, one is cis to that oxygen, and one is trans to that oxygen. Those are different magnetic environments, so they have different signals in the NMR. But if you heat it up, they begin to coalesce. 65 degrees, you get this broad singlet, and at 130 degrees, it starts to sharpen up. The two lines merge. Why is that? Well, there's enough energy at higher temperatures to rotate around that bond, okay? It turns out by analyzing the line shapes here in the NMR, and you can do theory on this calculations, rotation around an amide bond requires about 25 kcals per mole. And at room temperature, you don't have that. Thermal energy available at 25 degrees C is about 21 kcals. So you'll have slow rotation based on the NMR timescale, and you'll see these two signals at distinct spots due to the amide resonance. So we'll get into the structures in a second. That'll make more sense. I throw this in too. You've seen this graphic before. All these drugs, and you can analyze here the different derivatives of carboxylic acids. Here you see a carboxylic acid in aspirin, but you also see the ester, right? Acetate ester. Penicillin, you see the four-membered amide bond there. We'll call that a lactam. Carboxylic acid, oh, there's an amide also there. There's 3. Cocaine, 2 esters, right? There's none in AZT, although you call these carbonyls here the pyrimidine, you could say, oh, that's an amide-like thing, Yeah, same thing there. Sulfonamide down here, we won't do sulfonamides. Viagra has a sulfonamide, there's an amide there. Let's see, FK506, the immunosuppressant drug used for organ transplant treatment. There's an ester there, oh, an amide there. That's a regular ketone, that's not a derivative of carboxylic acid. Let's see, a couple there maybe. Thioamide, we won't do thioamides. There's a regular amide right there, benzamide. Taxol, the anti-cancer drug, there's an amide, ester, an ester there, a couple more esters down here. So they're ubiquitous, we can say. They're all over the place in drugs and biology, so we need to understand those. Here's fat metabolism. We'll get back to this later. Formation of esters from glycerol. Here's a 3-carbon trialcohol, glycerol or glycerin. First, it's phosphorylated, and then these thioesters with acyl carrier proteins in the R groups are long-chain fatty acid esters. These can be 16, 18 carbons long. Originally forms that, and if you put on a third ester, this triester here, or acyl triglyceride, that's fat or adipose tissue material in the body. So that's stored energy there. Adipose cells are essentially just bags of oil, this fat material here. And then we have the formation of the lecithins, which are the acyl phosphatidylcholines, 2 esters, and then the phosphate ester with the ammonium salt here, the ethyl group. This whole thing's called a choline group. This is the polar zwitterionic head group. We draw them as cartoon form. And then what are these 2 squiggles here? It looks like a frog, right? These 2 are regards to the long chain fatty acids. And this is the structure of the lipid bilayer membrane of all cells, both higher animals and simple single cell animals. Microorganisms all have this motif for forming these barriers between the outside and the inside, right? And they're held together with non-covalent forces, simply the hydrophobic effect. We got the nonpolar interior and the outside polar group. And they're formed with these acyl transfer agents, okay, from thioesters, and we'll revisit that. The oxygen esters are more stable than the sulfur esters, and that's kind of the basis for why those form. Okay, yeah, we'll get back to some of the applications. Let's go here to the sideboard. And before we jump into 22, I guess, we've got to review a little bit from chapter 21. So if you want to pause your video and try these, you can. And we're back. Let's see what the answers are here and see how you did. What type of reagent here? Secondary amine with a ketone. So what is this? It's going to be, yes, an enamine, not an imine. You should know the difference between enamine and imine. Why is it an enamine? Well, it has the alkene right here. And why? Because it's a secondary amine. You have the two alkyl groups. You can't lose a second proton off that. If it's a primary amine, we could, and we'd have the imine. But no, we lose water right here. Okay, so now that mechanism. Let's see if we have a methyl acetal here. We have the diether on the same carbon. So if we have water and acid, we can hydrolyze that back to acetone. And what's the alcohol here? Yeah, methanol would come off, okay? Make sure you can identify the alcohol that formed the acetal in the first place, right? That would be excess methanol and catalytic acid going back that direction. Okay, what's this? We have the phosphorane, the Wittig reagent with an aldehyde here. And so we're going to form the alkene. And cis is the usual product, but again, if you draw trans, that's fine. But connecting it up there, right? We have the nucleophile. Make sure you have the right number of carbons. 4 carbons there. There's a carbon right there. 1, 2, 3, 4. And then 2 for that. Don't worry about the triphenylphenyl phosphine oxide byproduct. That just washes away. We're focused more on the product there. And then we have this one, benzaldehyde with sodium cyanide, HCl. Yeah, that will form what? The cyanohydrin. Okay, so how do you do on that? That's a little review of stuff. Let's get into the main event here, which is the reactions of the carboxylic acid derivatives now. And all of these derivatives have this basic group, an acyl group. This is the acyl group, okay? So maybe I've been saying that. The carbonyl just refers to the carbon-oxygen double bond, okay? The acyl group has something on the side. And then, of course, here, in chapter 22, we're looking at all these derivatives where X can be very diverse. Chloride, another carboxylate for the anhydride, oxygen, hydroxide would be the carboxylic acid, of course. All of the mechanisms follow the same thing. So we're going to have a nucleophile, okay? And nucleophiles want what? They want a nucleus. So the electrophilic thing is the partially positive carbon of the carbonyl. So let's go ahead and attack that, push the electrons up. And, you know, this should be very familiar now to you, right? So all of them will follow this pathway. So here's our tetrahedral intermediate, sp3 hybridized. And the molecule has a choice here now. Because we have a non-carbon or non-hydrogen group here, this X group, it can leave, okay? And depending on how stable the resultant anion is here, will tell us what kind of a derivative we can make. So here's our new product, a new derivative of carboxylic acid plus X. And that has to do with what? How stable that is. With chloride, that's very stable because it comes from the strong acid. Coming from nitrogen, if this was N minus, that would be very unstable. Chloride's much more electronegative than nitrogen. Nitrogen is what, 2.8 on the Pauling scale. Oxygen is 3.5. Okay, so that's a better one too. So that's why esters are more reactive than amides. But we'll look at some of the other factors here. Now, the key reaction is this. So you can take carboxylic acid, and a lot of times we abbreviate these R groups. What's the R group? Well, it's some other alkyl or aromatic group. It's an old German term, radical, for the rest of the carbon chain. You don't need to worry about that. But let's see. So sulfur, thionyl chloride, SO what? SOCl2. The reagent looks like that. Like I said, your book has the mechanism for this. But if you treat carboxylic acid with thionyl chloride, you can make the acid chloride. And from that, you can make all the other derivatives, all others, okay? And so we have the acid chloride on the far left on that graphic, and that means it's because it's more reactive, chloride being the negative stable anion leaving group, we can make all the others. And so you can look at the hierarchy of derivatives and say you can make any one to the right from a given compound in the middle of that chart, okay? But for example, amides, which are the most stable, you can't easily convert those back to an ester or a thioester and anhydride. How do you deal with amides then? Well, all of them can be hydrolyzed with strong acid and base back to the carboxylic acid, and then you can remake the acid chloride and then make anything else. So all of these can be interrelated. And that's the confusing part about this chapter, keeping track of the reagents and the reactivity hierarchy and how it goes. Before we get into the reactivity, let's do a little on naming, and not a lot. We're not going to give you a bunch of complicated structures to name here, but you should know enough about this. So acid chlorides are named as alkanoyl, and you take off the IC, alkanoyl halide. We'll stick with chloride, okay? They're the most common ones. Yeah, there are acyl bromides and fluorides. The bromides are more reactive. They're corrosive. We don't deal with them. The chloride, the alkanoyl chlorides are the most efficient ones. So what would we call this? We call this ethanoyl chloride. Now, most chemists don't call the 2-carbon group that. We call this acetic, right? Acetic or acetyl chloride. And again, you take off the IC here in this case, and ethanoic acid. So yeah, you take off the IC and add the YL chloride. And same thing with acetic. Acetic chloride or acetyl chloride becomes the name of that. So this is the IUPAC name, but this is the common name that you would typically use. So how about this one? Well, that would be butanoyl. And that oil, or oil, if you're from Texas, oil, if you want to say it that way, no. Oil, butanoyl chloride. I won't draw out the rest of the name there. But yeah, how about this one? So if you have another common one here, that came from benzoic acid. So take off the IC. So this would be benzoyl chloride, okay? So take off the IC, common name for that. But yeah, systematic, this is the IUPAC name for these other ones here. Okay, I think that's enough on that one. How about anhydrides? Where we have 2 acyl groups on an oxygen, and they come from 2 carboxylic acids. You'll see that in a second. This one would be named ethanoic anhydride. So yeah, ethanoic. So we're using the whole IUPAC name for the acid and then putting anhydride at the end. Yeah, there is a space right there. But you know, ethanoic again, no, it's acetic. It's from acetic acid, so it'd be acetic anhydride for this common one. Acetic anhydride is a very common reagent. We use it all the time. So these symmetric ones, you just name it for the acid and then say anhydride. How about mixed ones? You don't have to have them come both from the same acid. How about this one? What acids did this come from? So it's a mixed anhydride, we'd say. Here's what, 1, 2, 3. That would be propanoic acid, right? What about this one here? Methanoic acid, or you remember the common name for methanoic acid? Yeah, formic acid. So how do we name this? Well, you just put the two together. Methanoic. So this would be methanoic, propanoic, and then anhydride. And you draw out the whole anhydride name. Or you could call this formic propanoic anhydride, okay? I think that's all you need to know there. Let's do esters. Esters are a little more complicated and a little more fun, I'd say. Esters or this basic structure here. And you've got two alkyl groups, right? Well, I guess in anhydrides we had two also, but these are different, right? Here we have an alkoxy group here, this O singly bonded to a carbon. And then we have the acyl R group over here. So this what? This comes from a carboxylic acid. And this comes from what? This comes from an alcohol. Yeah. So the basic name here is alkyl alkanoate. And the O8 maybe sounds familiar. We use that to talk about negatively charged species, nitrates, aluminates. So this 8 thing kind of sounds like it's an ion, but it's not really. It's referring to one part of the ester, and the alkyl is referring to another. So actually, this alkyl here, this prefix part, and yes, there's a space right there. This is referring to the R prime group, the alkoxy part. The alkanoate part here is actually referring to this side of the molecule, okay? So you've got two parts of the molecule to name here. Let's look at this one. So how would we name this? Well, we've got an ethyl group here, okay? That's the prefix part. And then we have what? Ethanoic, okay? So it came from ethanoic acid. Oh, but wait a minute, ethyl, this came from acetate, right? So we take off the IC and add ATE here. So ethyl acetate. This is a very common solvent. We use it all the time in the lab. But that's how we name it. The ethyl part here is referring to that 2-carbon alkyl piece. And then the acetate or ethanoate is referring to this whole thing here. Now be careful. You count the carbonyl as part of the parent name for the alkanoate here. Students commonly leave that off. So let's look at some other ones here. How about this one? Another ethyl. Oh, and this one has a more complex alkanoate to it. It's also ethyl, but what's this here? 1, 2, 3, 4. Oh, it's a butanoate. Okay. And what else is on the butanoate? Well, this is the 1 position. 2, oh, 3 methyl. Okay. 3-methyl butanoate. Ethyl 3-methyl butanoate. And that's about as complicated as we'll get to. It's a relatively simple one. This is a volatile, pleasant-smelling compound. The carboxylic acids themselves are sour, nasty-smelling compound. But if you make the esters, this is the essence of apple. So yeah, if you distill apple and make the essential oil from the apple material, the ethyl 3-methyl butanoate will be the major compound you'll actually smell. It has a pretty good vapor pressure to it. And why would they have the ability to have a lower melting point than the carboxylic acid? Right, the carboxylic acid can hydrogen bond with itself. It's very polar, whereas here you don't have the OH group anymore in the ester. So these become these volatile oils that are pleasant smelling. Let's look at a couple more for the fun of it here. How about this one? And be careful, you know, how the ester is drawn there. We need to name the alkyl part out here on the O singly bonded part, right? So what's that? Oh, that's isopropyl. And isopropyl's fine. That's accepted by the IUPAC. And what's our alkanoate? Well, it's methanoate, or what would we call it? Formate, okay? From formic acid. That's the common name. But yeah, isopropyl formate. Is that one of the compounds in nature with a nice odor? No, I don't know what it is. Let's get to one where it is. So how about this one? And we can use a common name here too. We'd call this a 3-propenyl group here, or that's an allyl group. Okay, this 3-carbon thing with a double bond here, allyl is the common name for that. It's accepted by the IUPAC. So this is allyl what? Allyl 1, 2, 4, 5, 6, allyl hexanoate. And does that have a odor to it? Oh, it's pineapple. Okay. And how about this one? Allyl heptanoate. Okay, allyl, but this has 7 heptanoate. Yeah, verify that you've got the 7 here. And you count the carbonyl, right? 1, 2, 3, 4, 5, 6, 7. Yeah, allyl heptanoate. This is the essence of what? Bananas. Okay. Yeah, so kind of fun. All right. Like I said, the pitfall here is making sure you name the alkyl and the acyl part correctly. Let's name this one. And let's see if you can do this one. And let me get a couple of them up here. And how about this one? Yes, those 3 of them that are all kind of closely related here. So try those. You want to pause your video? And we're back. Let's see what the name is here. Let's do this one first. So what's on the alkoxy part? Ethyl, right? Ethyl. And what is the alkanoate? Right, it's benzoate. Okay. So ethyl benzoate. Does it have an odor? Yes, it has a medicine-y smell. Smells like medicine. Okay. I'm not sure why you'd want that flavorant. Well, benzoic acids and benzoates are actually preservatives. They're actually added to food sometimes, not to food, but to certain medicines to keep them shelf stable. So some issues there, but yeah, that's the smell. Ethyl benzoate. Make sure you get the name straight. But what is this one now? Let's see. What's the alkyl part here? Well, it's this whole part here. Do you remember the name for that? Right, that's benzyl. Benzyl. Benzoic acid. The benzyl group is this extra carbon, extra methylene carbon with the benzene ring on it. If this was directly attached to benzene, that would be a phenyl group. Okay, but this is a benzyl group now. And what's the alkanoate? Yeah, acetate. So yeah, this is benzyl acetate. Notice the structure. We're changing where the ester is there. These are the same formulas, okay, the same ratio of atoms, but very different compounds. What's the smell here? Benzoacetate. Oh, this is pear smell. Okay, so much more pleasant smell than that one. So we wouldn't want to mix that up if you worked for a flavor company. Yeah, that'd be a bad thing to mix up. And how about this one? Very similar, I guess. Yeah, still have 3 carbons here, but they're part of that. And let's see, what's the alkoxy group here? Yeah, this one is phenyl. Phenyl, and what is the 3 carbon here? Well, propanoate. Okay, so yeah, fun with esters. Does that one have a smell? Oh, that's cherry smell. Wow, quite a range there. Pear, cherry, medicine-y smell, and they're all the same molecular formula, but it's where the position of the ester is and how they affect what your olfactory receptor in your nose. We're not going to go into that, but it's a structural thing of how it binds to that protein receptor, which is kind of fun to think about. But coming out of the names, use the name to help keep track of the structure, and that will be important for the reactivity of esters also coming up. All right, a little more on nomenclature, sorry. Amides. Let's see what we need to know here on amides. These are named as alcan. So alkane, take the E off and say amide. Alkanamide or alkanamide if you're British. Alkanamide. Yeah, alkanamide. Amide, amide, tomato, tomato. However you want to pronounce that. Make sure you get it right. Take the E off and add amide here. And remember, the carbonyl is counted as part of the parent here. Okay. So let's see a couple examples here. What would we call this? Yep, that comes from propanoic acid. So this is propanamide. Okay, not bad. How about this? It looks kind of funny, but no, that's a carbonyl on the nitrogen. So this is indeed an amide, and it's just the 1 carbon thing here. So this is formamide. And that's from the common name. Take the IC off, formic acid, and add amide. Okay, you could call this methanamide, okay? But yeah, propanamide there. All right, how about this one? What are we going to do with this? because you don't have to have just hydrogens on the amide. What about that one? So this is a little bit different. And the naming of these alkyl amides, where we have an alkyl group on here, is similar to how we name the esters, I think. But you have to put in the prefix here where that new group is. N-methyl, okay, means on the nitrogen of the amide is where this alkyl group is. N-methyl, and then what is this? Propanamide. Now, why do we have to say N and then where the methyl is? Well, we could have a methyl propanamide. We could have an extra group here on the parent, right? On the carbonyl part. So this N designation says it's out on the nitrogen of the amide. Whereas if there's other designations here, chloro or alkyl, whatever, on the chain here, they would be out here on the chain. And those wouldn't need the N designation. You only need the N designation for where they are on that. Let's look at just one other example here. How about this one? Oh, and let's have a little fun with it. Try that one. What would you come up with there? Well, we've got two methyl groups now, so we actually have to have NN, meaning both of what we're going to say now are on the nitrogen. And these are both the same, so NN dimethyl, okay. Now, if these were different, you can have different alkyl groups on the amide, then we'd alphabetize them. But they'd be here in the prefix with N's in front of them, okay? And then what's the parent here? Butanamide. And what else is on the amide? 1, 2, 3 position, we have 3-chloro. Okay, so 3-chloro butanamide. I didn't specify whether it's R or S. We could have that designation there. Maybe this is racemic, so we'd say plus minus NN dimethyl 3-chloro butanamide. Okay, and that's more complex than you'll get to. Don't worry about that. All right, let's look at nitriles or cyano compounds. And, you know, we call them either cyano or nitriles, okay? And, yeah, sorry about the two names there, but they're commonly used. And there's a lot of different ways to name nitriles. I'm going to show you all three ways. And, yeah, I'm not sure. The IUPAC name is alkane nitrile. Okay, yeah, and sorry, you can blame the IUPAC for this. There's no space there, and it's the full name of the parent, alkane nitrile. And your parent, including what the triple bond is included in this parent name, okay? That's one way to do it, or you name it as an alkyl cyanide. And in this case, this common way, when you say alkyl here, that's not included in, in that one. So that makes it a little bit different. And there's another way, alkanonitrile. Alkanonitriles, where you take the IC off, and that's for the common names like acetic, Seto Nitrile, we'll see in a second, or Benzo Nitrile. Or alkane nitrile, or alkyl cyanide. Wow, okay. Let's see a specific example, and we'll keep it simple, but yeah, it's good to go over, I think, a bunch of these anyway. So the simplest one here would be what? Propane nitrile. Okay. How else would you name this? Well, you could also name it ethyl cyanide. Now, that's the common name for it. And again, the ethyl is just referring to what's on the cyanide, right? Yeah, if that's not confusing enough. And then we've got the third way to name it. This would be from propanoic acid, right? Instead of saying ic acid here, then we say propanonitrile. Wow. Pick your favorite one. The simple ones are usually just named like that. Unless it's a solvent, usually that's the way it's named, but that's actually the IUPAC name. So sorry about that. Let's show you some of the common cyanides and what their names are, maybe, and we'll leave it at that. So how about this? This is Seto Nitrile. Seto Nitrile is a common solvent. You could call that methyl cyanide, but no one does. Everybody calls it Seto Nitrile, and that's because of that third way to name it. How about this one? This is another common solvent. We actually use it in our lab quite a bit for some high temperature Diels-Alder reactions. It's a high boiling, a relatively polar solvent, but it's non-polar enough to solvate things, so it's a useful solvent. What's this called? It's called Benzo Nitrile. And that's using, again, the common name. Take IC off and add nitrile. So Benzo Nitrile. And this is referring to that carbon. It's including it in the name. The benzo group, the benzyl group includes that carbon. Same with aceto. You're including that carbon there. So yeah, don't let nitrile or cyanide chemistry trip you up too much, although it probably will. Let's see. How about some cyclic examples? And these cyclic examples, we need to back up to esters, cyclic esters. These have some funny names, actually. I don't really like the way these are named. This is alpha, beta, gamma position. And this is called a gamma, not after your grandma, not after gamma or gammy. This is gamma, the Greek letter, gamma lactone. And I think that's an unfortunate name because it sounds like it's what? A ketone. It's not a ketone. A lactone is a cyclic ester, okay? This is an ester group. They're actually very common. We'll show you how some of them are made. It's a 5-membered ring for the gamma one. Let's see, is there an alpha, beta, gamma, delta lactone? Delta lactone would have this name. And so what would be its structure? Well, it'd have another carbon. So it'd be that. And this would be the alpha, beta, gamma, delta position. Okay, and that's where the thing connects back to form the lactone or the cyclic structure. Okay, know how to just name the common 5 and 6 ring ones. There are beta and even alpha lactones known, though. Let's look at cyclic amides now. So a cyclic amide would be something like this. These are called lactams. A tam, not a tam o'shanter hat in Ireland. No, we're not talking about that. Or a tam hat that you wear in marching band. No, we're talking about a lactam, which is similar to the lactone structure. But what's this tam thing? Well, it's a cyclic amide. And let's see, alpha, beta, gamma. Yep, this is gamma lactam. Let me show you a beta lactam, because these are common in drugs, in penicillin. And we'll see a number of these structures when we look at penicillin and how they react. So at the alpha, beta position, it's a 4-membered ring. They're relatively unstable. In fact, they react very quickly, and they'll acylate a certain enzyme involved in bacteria metabolism. So it's the basis of action of the antibiotic, actually, the beta-lactam. Anyway, be aware of those names. Sorry, there's so much nomenclature there. Let's get into some reactivity. I think we're okay on time. We got a few minutes, couple minutes. Let's at least start the first reaction here, and that's going to be acid chlorides. Now, these are very reactive, okay? And we're going to compare the reactivity here at first with water. If you put an acid chloride in water, it's done in minutes. The rate constant here, K, has a rate of 10 to the 11th events per second. That's almost diffusion controlled. So every time it collides with a water molecule, it's going to make the carboxylic acid and what? HCl. Okay, it's going to make the solution very acidic. Okay, you're going to see the pH drop, and it's going to be super reactive. Now, why is that? Let's look at the structure here. So it's a carbon-chlorine bond, okay, and a pi bond. And we know all about the pi bond, sp2 hybridization and everything. What's on the chloride? Well, lone pairs, okay? Well, we could think about what's the interaction between this chloride and this carbon here. First of all, how long is this bond? Let's see. It is relatively long. It's 1.8 angstroms. A typical carbon-carbon bond is what? 1.5 angstroms. Double bond is, 1.35. So 1.8, that's a super long bond, okay? And plus, this is in the next row down in the periodic table, right? So size-wise, if you look at these p atomic orbitals, these lone pairs here in chloride, compared to the p atomic orbital on carbon, you have this longer distance here. You don't have the ability to resonance stabilize that. In fact, what type of a bond is this? Well, it's a polar covalent bond polarized toward the more electronegative carbon. So what does that do to the reactivity? No resonance here because of the size difference between chlorine and carbon, and very electronegative. So yeah, nucleophiles are going to pile in here very quickly and attack, well, actually not the pi bond, it attacks the pi star here. That's the empty bond here. And then we go to the tetrahedral intermediate, and we got our nucleophile and chloride on there. And of course, the pair of electrons can come back down and give us the product, okay? Very quickly. And like I said, water itself, super high rate constant. In fact, this reaction is done in seconds, okay? Very fast. Let's compare that to the next one here quick, and then we'll end the first hour. Let's compare this to anhydrides. If you have an anhydride here, acetic anhydride, react this with water. They all react with water, right, to go back to carboxylic acid. It'll be 2 carboxylic acids in this case. This reaction, rate constant wise, is 10 to the 7th. It's done in minutes. It's not as reactive as the chloride. It's a little less reactive, but still it's super reactive, okay? Why? Let's look at the structure. Again, we've got pi bonds here, and we've got the carbonyl, and we can attack either one with our nucleophile, right? And that's polarized the same way. Well, what do we have here? We have these lone pairs, and yeah, one can be in a sp2 hybridized orbital where we've got a p atomic orbital with one lone pair that can resonate, and then one in the sp2 hybridized orbital. So what can this do? Well, it can resonate here, okay? And that will mitigate the reactivity because it's donating electron density in here. So unlike chloride, where we say there's no resonance overlap, it's a long bond, this is a shorter bond, and size-wise, the oxygen, of course, can resonate there. So that slows down the reactivity somewhat. But again, this is still a polar covalent bond, right? So that's increasing the reactivity inductively here. It's slowing it down a little bit by resonance. So those are really 2 effects, right? Right there's the inductive effect, and here's the resonance effect. And all reactions are combinations of those 2 factors, okay? So with chloride, we had that strong inductive withdrawer and no resonance, okay, which meant super high reactivity. Here we've got some resonance, but we still have the strong inductive thing there. And same thing on the mechanism, and we'll get to the details of that later there. But yeah, super fast. And then we'll do esters and amides here in a second to start out the second hour. So let's end it here, give you a little break, 10-minute pause for the cause, or as long as you need, and we'll be back here for the second hour today. Thank you.